Welcome all my dear students. So this is lecture 6A of CS 302 data structures. This lecture I have divided into two parts. In one part we are going to see about the insertion operation in array and the insertion operation in a single linked list and their complexity difference. In the next lecture we will be seeing the deletion in array and the deletion operation in single linked list along with the complexity. So let us start with the insertion in array first. Now, if we are talking about an insertion algorithm, an insertion operation in array or linked list, there can be three places in which the insertion operation can be done. One is at the beginning of the array or linked list, one is at the end of an array or linked list, and the last one is at the middle of an array or linked list. And in case of middle of an array or linked list, what we can have is that, so a particular node's value can be given and you may be asked to add before that given node value or after that given node value. Similarly, we can also be given the node count. So suppose I have been told to insert an element into an array after index 3 or before index 3. So these are the three scenarios in which we are going to discuss the insertion operation in case of both array and linked list. So let me first start with the array insertion operation and then we will be going to the case of single linked list. Now let us see the example of insertion operation in array at the beginning. So we already have this array. Let us assume we have this array and we have declared the size of this array to be, so we have declared the size of this array of, because we are storing integer data, so let it be something like A5. So out of 5 elements, how many elements we have inserted? Only 2 elements. Now I want to insert at the beginning. So if I want to insert at the beginning, what is going to happen? So we have to shift the elements to the right. So the elements should be shifted on the right hand side. So 10 will be shifting here to index 1, 20 will be shifting to index 2. So if we shift the elements like this, then this space will become empty. So it will become something like this. So once I shift the elements to the right, so this will become 10, this will become 20. That is, we made this place empty. Now remember, when we are implementing this, we will not be able to empty the space because in array we do not have any concept like emptying the space. What we can do is that we can overwrite the 0th index. So we can copy the content to one position on the right and this space will be having the value of 10. So which we will be overwriting with the new value. So this is having a 10, but we will be overwriting it. Now let us want to insert a value. So my val, which I want to insert now, be 30. So what I do? I simply insert it. So always the insertion in case of the, at the beginning, in case of array, the insertion will always be at the, so insertion at the beginning will always be at the index 0. At the beginning means insertion will always be at the index 0. And if we have to always insert the element at the index 0, what will happen? We have to shift the elements on the right hand side. So this shifting operation in case of array, this shifting operation takes a order of n time. And therefore, the complexity of insertion of a new node or of a new value in array is order of n. The simply inserting the elements, so see, if we are doing it, simply inserting the value is order of 1, but along with the inserting operation in case of array, what is associated is also the shifting part. This shifting part takes a order of n time. Therefore, we tell the insertion operation in array at the beginning is order of n. Now, let us check the scenario of at the end or at the middle. So, what we are going to do? Now, we are going to insert at the middle of the array. So, at the middle, I told we can have two things. One is after a given node value or after before a given node value, or after or before a given node count. So we can either have to insert after two elements, so that is a count, or we will be told to insert a value 30 after the given value 20 or after a given value 10. So what happens if we want to do that? See, again, if I want to insert a value after 10, so this scenario, so I will just remove this part. What happens here? So I want to insert a value after 10. So what I will do? I will keep 10 as it is, but I will make the position after the value 10 empty and shift all the elements to the right again. So again, there is a shifting operation required, which in the worst case will be taking an order of n time. So whatever be the value after which we have to insert, if it is in the middle of the list, again there will be a shifting operation. So at the beginning, it's somewhat kind of a special case of at the middle, because at the beginning, what we are doing is we are inserting a node at the index 0. Now, if we have been told to insert an element before a value 20 or before a value 10, then it becomes equal to the insertion at the middle. So again, at the worst case, it takes an order of n time because of the shifting operation. Now, if we are talking about at the end, if we are talking about the insertion algorithm at the end, so what happens here? First, we are going to search the list. That means here the operation will take place we are going to first search the elements, and then we are going to reach the last node. So I want to insert the value 30. What I will be doing, I will be searching, start my search from 0 and go till the position where there is data in the array, and I find the empty space, I put my data. So this will become 10, 20 and 30. So in the insertion, if you want to insert an element at the end, the requirement of the shifting operation is no more there. So shifting is not required in this case. Only what is required is searching the list, that is traversing the list, reaching the last node and putting the data. So the complexity, we can define it. So the complexity in case of the insertion at the end, we can define as the search or as the traversal time plus order of 1. We can always share that. But if you are looking for the, again at the beginning, insertion at the end can be termed as a special case of insertion at the middle, because we can tell into like at the end can be represented like insert a value 30 after a given value 20. So it becomes somewhat similar to the insertion at the middle. So at the worst case, it is going to be again order of n. So we see that insertion operation in array in the worst case is order of n. Now another problem exists in case of array, that is, suppose I have declared the size here to be 5 and my list is already full. So let my list be something like this, 10, 20, 30, 40 and 50. Now again I ask to insert a value something like 100 maybe. What will happen? If I am implementing this array like statically or dynamically, I have to again change the size of the array. If I don't change the size of the array, then in this case, there will be an overflow condition. Well, if I declare the array to be initially of a high size, like maybe int 1000, so I have allocated space for 1000 elements statically, and then if I don't use the 1000 spaces, then it will be a wastage of memory. So generally, array is disadvantageous from these 2 points. So the first point in case of array is requires more time for insertion, which is order of n, and the other is could lead to wastage of memory space if most of the memory spaces are unused. Now this second point can be reduced if you are using some kind of dynamic memory allocation using malloc or calloc, but still there, depending on the size of your array, you have to again reallocate memory space if your program demands more. Now when we talk about the linked list, we will be seeing that both of these operations, both of these disadvantages is not there in case of a linked list. Now if I talk about the space complexity of array, so the space complexity will be order of n. Why? Because in case of the space complexity, we see that if we have to insert n number of elements into an array, the number of memory spaces which will be reserved will be equal to memory spaces reserved for n number of values will be equal to n into size of the data type. So if you are storing it to be of integer type, then it will be n into 4. If it is for 1000 elements, so 1000 into 4 and so on, that many bytes will be reserved. So if you have to store n number of elements, the space complexity will be order of n. Now let us go and check for the algorithm for all the 3 cases at the beginning, at the end and at the middle of a linked list, and how we can improve over the array. Now let us see the same insertion algorithms in case of a linked list. So for the input to any insertion algorithm, it will be the list and the value val which we want to insert, and the output will be the new list with the added node. Now before going to that part, let us see this. If we want to implement a linked list, how we are going to do it? So for that, we have to define our struct node. So this will be a structure node because it will have two different type of data types. One is a data, which can be of int, floor, char, etc. I'm showing the examples as integer data, and the other will be a pointer of the struct node type. So what does this pointer means? This pointer basically means that, so this is my node. So this is my node. This part will have the data part. So this is the integer data part. And this part will be a pointer to a next node. Now, why the type of this pointer is struct node? Because next is going to be up again, the names I have given, you can give any other name what you want to give. So the variable names depends on the programmer who is going to do, but this is the most standard notation you can find anywhere. So what this next pointer will do? It is again going to point to a node which again consists of these two data. So that's why the pointer is of type struct node, because it is going to point to another struct node data. Now, that's why linked list is known as abstract data type or ADT, because when we are writing the algorithm and when we are actually implementing it, so we hide the information of the implementation in the algorithm. So that's why it is known as ADT. Now let us look at the first step of this algorithm. So the first step here is, if abel is equals to null, what does this mean? Let us see this. So this, let us assume that this is the OS memory, and abel is a pointer which is going to point to the very first available memory space in the OS. When I show you the implementation of linked list, then I will be telling you how this part we can implement in any programming language. So for as of now, you remember that abel is a pointer which is going to point to the first available memory space in the OS. Now, if this is empty, that means if there is no available memory space in the OS, that is in the operating system, what it is going to report? It is going to report an overflow condition. That means the OS doesn't have sufficient memory space to allocate to a given node. Because you can see that whenever we are doing some kind of thing, it's basically allocating some memory space. So if there is no memory space, it is going to report an overflow condition. Now, if it is not an overflow condition, then what we do, we write new node equals to abel. That means this memory space which abel is pointing to will be given to the new node. So what does this mean? It means that it is pointing to some memory location, suppose 1000. So this is a memory location 1000, that 1000. So this node has been allocated here. So whatever will be the size of this, so we know that size will be 4 because integer data is 4 bytes. And again, a pointer is a 4 bytes because it is an unsigned integer. So 4 plus 4, 8 bytes will be reserved. So now at the next place, what will happen? Abel will be pointing to 1008 location. So at the next part, Abel will be pointing to maybe 1008. So this is from 1001 to 1007 will be allocated for this node, and then Abel will be pointing to 1008. So we can keep on continuing this. So this is what the step abel equals to abel arrow next. So again you see the memory spaces in the operating system are maintained with the help of a linked list. So abel is a pointer which is pointing to the first available memory space, and all the available memory space are linked together with the help of a pointer. Now, if we go to the next part, what is there? So we have a value. Suppose I want to insert the value. So this value, let it be 30. I want to insert it. And where I want to insert it? I want to insert it at the beginning. Now, here there is a pointer which is known as a start. So what does start contains? Start always points to the first node in the linked list. So this is my first node in the linked list. Here, start is going to point. So again, it is a pointer, And if a pointer is pointing to a data type of struct node type, then start will also be of the type struct node. So what does start contains the address 200? It's a pointer. Start is a pointer. So what will be the next step? New node arrow data equals to val. That means in the data part of the new node. So this is my new node. In the data part of the new node, I want to have the value 30. So I have written 30 here. Now this is the first node. So what happens? So how we have to link it? So basically, we have to link it like this. So start will be pointing to my new node. And my new node have to point to this. So previously what was the first node now becomes the second node. And the new node will become the first node. So what we can do? First we can write new node arrow next equals to start, because start is 200. So if I write new node arrow next, this is the next part. And this is the data part. So let me write down. So this is my data part of the new node. And this is my next pointer part of new node. So what happens? So in the new node next pointer, I copy the address of the start. So once I copy the address of the start, what happens? This was already there. This part was already there. Now this part linking is also over. So 200 is copied here. This also contains 200, so pointing to this node. And the next pointer part of the new node also contains 200, so it points to this node. Now what happens? So now we have to make this new node the start. So we write start equals to new node. So we remove, so this now this, if we write this line, this linking will be over, and now it will be coming down to this one. So you see, we have inserted a node at the beginning of the list. What will be the complexity of this algorithm? Now, if you look at this complexity, insertion in this case is only a few pointers change. Insertion in case of the beginning of the list, linked list, is only a change of few pointers. And changing pointer values is a constant time operation. That is, complexity of insertion is order of 1. Because we are only changing a few pointer values, which is a constant time operation. So insertion at the beginning of a list, linked list, is order of 1. Now let us see the insertion algorithm for a linked list at the end. That means we want to insert a new node at the end of a linked list. The input and output is same like in case of beginning of the list, and the first 4 steps of the insertion algorithm, any insertion algorithm, that is checking for whether avail is equals to null or not, and then assigning the available space to the new node, then making avail point to the next available memory space, and new node arrow data equals to val. That means adding the value at the data part of the new node. These 4 steps are common for any insertion algorithm. The change comes from the 5th step. Now, let us see how we can do that. Now, logically, what we are about to do is that this is my new node with the value 30. I want to insert it at the end of the list. Now, whenever there is some node at the end of the list, what we can see is that for the last node, the next pointer part is always null. That means the null indicates that there is no node after this node. So this is the last node. So if we have to insert a new node at the end, that means we have to check for the next pointer part of any node, whether it is null or not. If it is null, that means there is no node after the node and we can stop at that node. So that's why what we do, the fifth step, what we are going to follow is that because this node is going to become the new last node of the list, we can safely make the next pointer part of this node to be null because there will be no node after this new node. But then we have to start from the starting node because we have to start from the using the start pointer. The start pointer always points to the first node. So starting from the start node, we have to reach the last node of the existing list. For that, what we do, we take a temporary pointer called PTR. Again, this is a variable name. It can be anything which you wish. So we have to take PTR, a temporary pointer, and make it point to the start node. Because PTR is equals to start, that means PTR is also going to point to the same start node. And then using this pointer, we have to reach the end of the list. And what should be the condition for checking whether PTR is pointing to this node? That means whether the next pointer part of PTR is null or not. So if when it is pointing to a given node, if the next pointer part of that node is null, that means we have reached the end of the list. So the checking is whether PTR arrow next is not equals to null, then we go to the next one. So PTR equals to PTR arrow next. So let us see here. So is PTR arrow next equals to null? No, the address, there is an address 400. So we do PTR equals to PTR arrow next. That means in PTR, 400 is assigned. So let me write down here for a better understanding. So PTR now is equals to 200 because PTR is equals to start. Now what is there in PTR? Arrow next. So PTR arrow next is equals to 400. It is not equals to null. So it is not equals to null. So what we do, PTR equals to PTR arrow next means we copy the address of PTR arrow next to PTR. So now PTR becomes 400. So if PTR becomes 400, that means that PTR no longer points to this particular node, but now the pointer has shifted to this node. So PTR is now pointing to this node. Now what happens? Here we see PTR arrow next is equals to null. Yes, so that means we have reached the end of the list. Now what we have to do? We have to copy the address of this node, copy the address of this new node to this. Why? Because we want to link this node with this node, and if this node is the last node, so this node will be the one before the last node. So what we have to do, we have to take this address of new node and copy it in the next part of PTR. So that's why it is written PTR arrow next equals to new node. So once we do this, what happens? This part is removed, and here what is copied is 1000. So what does this mean? If 1000 is copied here, that means this link of the node is over. So we have linked it. So again, this node becomes the last node in the list. So again, if we look at the complexity of this algorithm, now here there are two things. There are two aspects of this. One is the search time, which we know is order of n in case of a linked list, as we have seen in the last class. And another part is the insertion. So insertion is order. So another is insertion time. So insertion time is what? Order of 1. Why? Because we are going to the last node using the search technique, which takes an order of n time. But when we are inserting the value, what we are doing, we are making few changes to the pointers. So basically there is a one pointer change. So because of this, the insertion time is a constant time, which is order of 1. We do not include the search time here because search time is taken care of separately. So the insertion time in case of the insertion at the last also for linked list is order of 1. Now let us see the insertion algorithm of a node after a given value. Now this is the case of insertion in the middle. I am discussing here one of the case, that is a given value, a value is given. You can do it for a given count of node, and you can also try it out for before a given node. Let the num value after which I want to insert be 20. The input to this particular algorithm will be 3. One is a list, the other is the value val which we want to insert, and the last one is the value num after which we want to insert the new node. The output will be the new list. For this algorithm, the first 4 steps will be common steps like any other insertion algorithm, that is checking for the available memory space. If the memory space is there, allocating it to the new node. So let the new address be 500, which has been allocated. Next, Avel will point to the next available memory space, and in the data part of the new node, we will be having the value copy. Now in this case, we are going to use 2 pointers. Why we want to use 2 pointers? Once I explain through the whole algorithm, I will be coming back to it. So let the 2 pointers be PTR. So PTR equals to start. That means PTR is equals to 200. PTR will be pointing to this node. And pre-PTR is equals to PTR. That means for this case, let me write down in short, PPTR will also be pointing to this node. Next, what we are checking, whether the PPTR arrow data is equals to num or not. So let us go to the first case. Is PPTR equal, the arrow data is equals to num? No. So what happens? PPTR equals to PTR. So PPTR remains. So what is the value in PTR right now? Let me write down here. So start is equals to 200. So initially PTR is also equals to 200, and PPTR is also equals to 200. Now we are checking for PPTR arrow data is equals to num or not, because it is not equal. Now what is happening? PPTR is equals to PTR. That means PPTR remains at 200. But PTR moves to the next location because it is equal to PTR arrow next. So what is there in PTR arrow next? 400. So it becomes 400. So how the pointer changes are taking place? So PPTR remains here. However, PTR moves away from here and it goes to this location. PTR moves to this location. Again, we are checking whether PPTR arrow data is equals to num. No, it is not equal. We can check. It is value 10. Well, we want the value to be 20. So again, the pointer changes take place. That is PPTR equals to PTR. So what is there in PTR right now? So again, let me write down here. So now PTR is equals to 400. So PPTR equals to PTR equals to 400. And PTR is equals to PTR arrow next. So what is there at the address? It is 100. So it is 100. So PTR becomes 100. That means PPTR moves from this location and it goes to this location, while PTR moves to this location. So this is PTR. Again, we check for PPTR arrow data is equals to num or not. Now it is equal. So we come out of the loop. Now what we have to do, so PPTR, so why we require 2 pointers? So 2 pointers are basically holding on to the 2 locations between which, or 2 nodes between which we have to insert the new node. So we have to insert this new node 40 between this node which is pointed to by PPTR and the other node which is pointed to by PTR. So what we have to do, we have to put the value of 100, we have to put the value, that is the address 100, in the next part of new node. So new node arrow next is equals to PTR, and in the next part of PPTR we have to put the address of new node, that is 500. So after we have gone through this step, we come here. So PPTR arrow next, that is in the next part of PPTR, we have to put the address this. So we remove 5 here and we put 500. So once this is done, so this linking is over and this linking is no more there because it is pointing to 500. And in the new node arrow next, we put the address pointed to by PTR, which is 100. So we write 100 here. So once we write 100 here, then this link is also over. So we have been successful in inserting a node after a given value now. Again, if we look at the complexity of this algorithm, the complexity will be same like in case of insertion at the end. So there is a search time, which in the worst case is order of n, plus there is an insertion time. Again, the insertion is a few pointer location and it is order of 1. So insertion algorithm, now if we look at this particular algorithm of inserting in the middle of a list, we can consider to be the conditions of insertion at the beginning and insertion at the end to be a special case of this. Because if we want to insert a node at the beginning, so that insertion can be like insert a node before the value 10. Well, if we want to insert a value at the end, it can be something like insert a node after a given value 20 or after a given value 30. So insertion algorithm in case of a linked list is a constant time which is order of n compared to the array which is order of n in any case except the last case. If we talk about the space complexity of a linked list, you can understand it is going to be order of n like array, because if we want to insert n number of nodes, naturally the space required for the n number of nodes will be equal to the n into